Hello. Today I will speak about automation in CCP4 Cloud. I will tell you about workflows. CCP4 Cloud is a new way to solve structures via CCP4 Suite. With CCP4 Cloud, we can exploit power of remote cloud computing, or alternatively, we can run cloud completely locally on user's machine if required. And major feature of CCP4 Cloud is effortless passing of the information between tasks when output of one task become input of another task, forming tree of tasks. And if you are not familiar with CCP4 Cloud, for detailed description, please see the tutorial via this link. It shall be available in the comments section as well. And we are constantly thinking how to make use of CCP4 Cloud easier and more efficient for various users, for structural biologists, for novice users, for experts, for busy industrial users. And the answer we got is automation of the routine tasks. And if you think there are two levels of automation are possible, at the level of the whole project, to help user navigate through the whole process of structure solution, or at the level of a particular task to help user with optimization of parameters for some particular program. So, automation for the whole project. It's called workflows. Workflows are in fact inspired by CCP4 workshops. At the workshops, we are teaching some steps that are required to solve the structure. And just imagine these steps just run automatically on your data. And this would be CCP4 workflow. You can think about workflow as some standard sequence of crystallographic tasks with some smart decision making in between. And this sequence of tasks unwrapped in the form of standard CCP4 Cloud project and tasks tree. And once workflow does its job, you can access all the task reports, clone tasks, rerun tasks, just continue working on the project manually. Essentially, you will get CCP4 Cloud project with number of tasks already run on your data. And if your case is fairly solvable, you will get solved structure. Fingers crossed. Please note that we don't aim workflows to give the final answer and to finally solve your structure. We rather aim at providing good starting point for the following work. And now let me demonstrate what it looks like. So let's start CCP4 Cloud Remote. Why CCP4 Cloud Remote app from CCP4 Suite. I will log in into main cloud with my credentials, and let's start a new project. Here we have new auto start mode, that's simplified mode for starting with one of the automatic workflows. Why not start with automated molecular replacement? So this is the list of available workflows, and for automatic molecular replacement, you only need your data and your sequence. As easy as this. Just provide reflections. We will use lysosome example, why not? And sequence for automated search. If your structure has ligand, you can provide SMILES code or 3-letter code for common ligands like ATP. There are no ligands for this case. So just let us press run button and see how workflow unwraps CCP4 Cloud project. Actually, you don't need to sit in front of your computer and stare into the screen waiting while workflow does its job. That's cloud. You can simply log out and go enjoy your lunch, do whatever you like. After half an hour, you can log in back and find results of automated workflow run in the cloud, ready to use. So, workflow has finished, and as you can see, it solved structure with R3 of about 26%. which is not bad. Now we can examine what exactly workflow did. It created a symmetric unit and correctly predicted number of monomers in the symmetric unit. It runs SymBot. That's a program that searches PDB for identical unit cells. If they are present, the structure will be solved by SymBot. We run it to make sure that this exact crystal form for your protein is not present in the PDB. So it's not present, then Mr. Bump is a pipeline for automated molecular replacement. It has solved the structure successfully. Let's have a look. Oh, it found quite a number of models with 100% sequence identity. It solved the structure to a free of about 30%. Then RefMac refinement. It ran 50 cycles of jelly body refinement to settle the structure after molecular replacement in your density. Then Buccaneer rebuilding rebuilds the structure. And another round of RefMac refinements. You may ask a question why there are several RefMacs run in parallel. But you see, that's a topic for a separate talk about verdicts. RefMac parameters optimization happens here. So another bit of automation. After that, waters have been fitted and another round of RefMac optimizations. And now automated workflow has finished successfully. And we strongly suggest to manually examine the structure before the deposition. We also run deposition task, mostly to show you validation report, so you can quickly examine quality of the structure obtained after workflow. Well, yes, everything could be improved. There are fewer Magellan outliers flagged. Clash score is a little bit high. Let's have a look. Why not start from the last RefMac and run code to just see what do we have here. This is what the structure looks like in code after automated model building. I would say it's not bad. So from this moment, you can just proceed manually. Yes, you can see straight away, for instance, this side chain could be fixed into the density. So something to play with. And again, I remind you that with workflows, we don't aim at solving the structure, and we don't aim at giving final answer. We aim at providing a good starting point, so then you can continue to optimize your structure manually. Another workflow I would like to demonstrate is simple molecular replacement workflow, this time with ligand. So what's the difference between automatic molecular replacement and simple molecular replacement? For simple molecular replacement, we assume that you have domain or structure of a homolog or any other search model that you can use to solve this current target structure. So let us use MDM example with unmerged data this time. We can use this structure to solve and sequence. This time we do have ligand and we can provide smile string to generate it just by copy and paste. You can fill ligand name here, or you can just leave it blank, it will be filled automatically. So let us have a look what workflow will do this time. As we provide unmerged data, it was correctly detected by the cloud, so it ran aimless to merge the data. And as you can see straight away from the statistics, completeness 75% doesn't sound good, isn't it? So even while project unwraps and automation is working, of course, you can examine all the log files here. Let's have a look what happened with our aimless run. Scaling and merging, and oh, statistics for AutoShell is terrible. I know why, because resolution is greatly overestimated here. Also, I know that latest batches of this data set are radiation damaged. So what can we do? We can clone aimless task with either this button or this button. And after cloning this task, we can specify parameters we like. So here we have batches from 1 to 60, and I believe batches 1 to 50 would work better. And in basic options, we can provide high resolution cutoff of 1.5 angstrom. Currently data to 1.25 angstrom. So I can modify parameter of this task. You see that clone task appeared in the tree. And you see now it's keep auto checkbox. If this box is checked, then workflow will continue from this task as well. If you uncheck this box, then a single task will be run. But what we want to run full workflow from this cloned modified aimless. So we are keeping auto, pressing run button, and let's see what happened. Please note that in the previous branch, it is still phaser running, trying to solve the structure from the previous merging attempt. Now completeness is 99% compared to 75% only. And statistics for our merge is again much better. So, but we still can run these two branches, they will run in parallel, and then we can compare. And both our branches has finished. As you can see, after proper merging with correct parameters, RefMag refined final structure to 25.7%, to a free of 25.7%, and with default aimless run, it's 27% are free only. So let's have a look. So first of all, a model was created from supplied PDB file, model for molecular replacement. And again, if default model did not work properly, you can rerun this step and specify another parameters for model generation. For instance, you can modify side chains via different protocols, etc., etc. Phaser gave a solution in a different space group. Those are enantiomorphs and aimless merged data to P6122. In fact, this is P6522, and workflow managed to automatically resolve this via phaser. Then model rebuilding with Buccaneer has been performed, and as R factors a little bit too high, a decision was made to try much longer CCP4 build rebuilding pipeline. Very often it delivers better results, but unfortunately not in this case. Again, after comparison of two model rebuilding programs, Buccaneer and CCP4 build, workflow made automated decision. Yes, apparently Buccaneer still proceeded better than CCP4 build pipeline, so it continued to unwrap the project from the Buccaneer point. Again, structure was refined with RefMag. Ligand has been generated by AceDrag from supplied smile string, and we can use ugly mole viewer to see the structure of the generated ligand. Ligand has been fitted, refined with RefMag, waters fitted, and another rounds of RefMag refinement. And here, in our second copy, started from aimless with manually modified parameters, essentially the same path. Buccaneer, CCP4 build, again Buccaneer performed slightly better. RefMag refinement. Let's have a look what fitted ligand looks like. And we even don't need to start good to examine the structure because ugly mole viewer is very useful and will display even electron density. And as you can see, well, I would say that's quite nice fit. Apparently one atom is a little bit out of the density. It shall look here, but apart from that, ligand is mostly fitted well. So there are still minor things to fix manually by code, for instance. This thing looks like the side chain is wrong rotamer. But again, for automatically solved structure, I think it looks pretty good. So let's check deposition report. What do we have here? Some Ramachandran outliers, but again, clash score is very reasonable. Sidechain and sidechain outliers and other outliers in the reasonable range. So not that bad. And again, I would say this is a great starting point for manual work. Let's have a look at experimental phasing with workflows. P9 example. Again, auto start mode. And automated experimental phasing with Crank2. Crank2 is absolutely marvelous pipeline. It will solve structure for you if the signal, anomalous signal is okay. So CCP4 Cloud works perfectly well with SCA files as well. For SCA, we need to provide wavelength. So to solve data with SAD, we only need diffraction data and a sequence for automated building. There are no ligands in the structure, and of course, we need to provide main anomalous scatterer, which is selenium in this example. And let's have a look what automation will do for us. So, great job is done by Crank2. Structure is solved to R3 of 29.4%, 137 residues built, and you can examine all the details here, like great contrast on hand determination step. Anyway, after Crank2 refinement with RefMag with parameters optimization, fitting waters, and another rounds of optimization with RefMag. Deposition report as before, and again, this is a great starting point to continue manual work on this project. And let me show you the last available at the moment workflow. We are thinking about making more workflows. That Dimple workflow. Dimple is a pipeline specifically designed for the cases when you determine multiple structures of the same protein crystallized with different ligands. So assumption here is that you have your reflection data, merge data in this case. You have your protein structure already solved, so you provide PDB file. Of course, you need to have sequence of your protein, and you can supply ligand not only by SMILE string this time, but also with ligand CIF definition. We optimize this pipeline for industrial users, and mostly industrial users have their ligands as CIF files. So just specify CIF, and let's have a look what we will get in this case. And this is it. Again, automatically we got salt structure with a free of 24.3%. Waters fitted, ligand fitted. Let's have a brief look. Again, we can just use ugly mole to quickly examine the structure. Looks not bad. Again, we can fix this one atom of the ligand, but majority of the ligand is fit nicely. Waters are there. If you have your protein crystallized with different ligands, you may opt for Dimple workflow to quickly solve all that multiple structures. And I think the demonstration is over. Please try workflows, and we are always waiting for your feedback. Thank you.